Hi everyone. We're still in section 6.3 about diagonalization in the textbook Linear Algebra Done Openly. And so now we're actually ready to define what this word diagonalizable even means. So as usual in this chapter, if we have a matrix which is square, so say A is an n by n matrix, we say that A is diagonalizable if it is similar to a diagonal matrix, which specifically means that there exists some invertible matrix P such that P, D, P inverse is equal to A. So we had talked about similar matrices previously. You can look at the link if you want to see some more about those. But a matrix is diagonalizable if it is similar to a diagonal matrix. Let's look at an example of such a thing. So let's take this 2 by 2 matrix A right here. It'll be the matrix 7, 2, negative 4, 1. And using the non-singular matrix P, which is 1, 1, negative 1, negative 2, this is in fact a non-singular matrix here. You can see its proposed inverse is right here, 2, 1, negative 1, negative 1. And I can verify for us that this is in fact, these are inverse matrices of each other. It's not too hard of a calculation. Don't forget the negative sign there. 2, 1, negative 1, negative 1. If we go through the multiplication, we're going to end up with 2 minus 1, we get 1 minus 1, we get negative 2 plus 2, and then finally we get negative 1 plus 2, which clearly becomes the 2 by 2 identity. So these are in fact inverses of each other. And so then compare this with, we have this matrix P, and then I have this proposed diagonal matrix D, which D is the matrix 5, 0, 0, 3. I claim then that A can be factored as the matrix P times D times P inverse, which you see the matrices right here. Now, one thing to remember is when you multiply by a diagonal matrix, if you multiply a diagonal matrix on the left, you're going to scale each of the rows by the corresponding value. So if you take this matrix right here, this product 5, 0, 0, 3 times by P inverse, this will have the consequence that you're going to scale the first row by 5, so you get 10 and 5, and you're going to scale the second row by negative 3. So multiplication by a diagonal matrix is pretty quick and slick. So this matrix right here is none other than just dP inverse right there. And then with these two matrices, you just do the matrix multiplication. This row times that column, you'll get 10 minus 3, which is 7. First row, second column this time, you'll get 5 minus 3, which is 2. Second column, first row, you get negative 10 plus 6, which is negative 4. And then second row, second column, you get negative 2 plus 6, which is 1. So you see the product right here. Now, I did want to mention that you can go the other way around if you wanted to. If you wanted to multiply these ones first, if you have a diagonal matrix, that's on the right, then you do scaling. You'll scale by 5 and by 3, but you'll scale the column by 5 and the column by 3 if you wanted to. Either one of those is okay. So this verifies that we do in fact have a diagonalization. This is the real McCoy right here, that this factorization works, and this shows that A is similar to a diagonal matrix. Now, why might someone be interested in a diagonalization? There's actually a lot of benefits of it. I'll just give you one quick application of diagonalizations that can help you with sort of numerical analysis of matrices. If you were to square the matrix A, so this is the same matrix from the previous slide. If you square the matrix A, well, since A is equal to PD P inverse, you could actually use that, so you get A twice. But you'll notice that if you have P or PD P inverse, PD P inverse, you could actually put the P inverse and the P together that shows up in the middle, and they actually cancel out, and you'll end up with D squared in the middle of P D inverse, P inverse. Notice this shows you that if A is similar to D, this also shows that A squared is similar to D squared. And this is actually a common fact. If A is similar to B, then A squared will be similar to B squared, A cubed is similar to B cubed, and all of the powers will be similar as well by this calculation, by this type of thing right here. And so, why would we care about this? Well, the thing is, squaring a diagonal matrix is a whole lot easier than squaring a regular matrix. Because it's a diagonal, to square a diagonal matrix, you have to square the diagonal entries. 5 squared and 3 squared, which are, of course, 25 and 9. That's not so bad to do. And then once you square the matrix, you'll times it by p, you'll times it by d, p inverse, excuse me. And since d squared will still be a diagonal matrix, one of those products just means scale the rows or scale the columns, whichever direction you prefer. So in order to, if you have a diagonalization in hand, the amount of difficulty of computing the square really just comes down to you have to be able to square real numbers. Not so bad to do. You have to square and scale the real numbers, and so it's really like it feels like one matrix product with a couple of multiplications along the way. Now, if you just have if you're just squaring it, that might not seem like a huge benefit. But what if you have a large power of a, right? What if a of k here is like, say, the 17th power? Well, if you wanted to do a times a times a times a times a times a 17 times, that's going to add up. You have to do like 16 matrix multiplications. But if you had a diagonalization in hand, you have to do a exponent for real numbers, an exponent for real numbers. That's not so bad. And then once you have those, again, you scale rows of a matrix. That's not so bad. And so you actually only have to do like one full-blown matrix multiplication. If you think of matrix multiplication as this expensive operation, it turns out that having a diagonalization can dramatically simplify computing exponents for matrices. This is, of course, if you have a diagonalization in hand. So this is just sort of a numerical benefit. There are other benefits, both computationally and theoretical benefits of diagonalizations. But let's sort of try to explore a little bit how one would find a diagonalization of a matrix. And so I want you to sort of notice the following observations here. So we had our original matrix A, which you'll, if you forgot it already, maybe because you saw a butterfly fly in front of your screen or something, we have A was the matrix 7, 2, negative 4, 1. In the matrix P, remember, again, it was the matrix 1, 1, negative 1, negative 2. If you focus on the first column of P, right? If we have a diagonalization, if A equals PD P inverse, this is the same thing as saying AP is equal to PD. And if we focus just on columns, right? If you take the first column of P, call it X, then this will tell you that X is this, you're going to scale that column X by some number, which we might call lambda X. If this diagonalization happens, it turns out that the ith column of P is going to be an eigenvalue, an eigenvector of the matrix A. And we can see this for our specific example, right? If you take A times 1, negative 1 right here, you work out the details, you're going to get 7, 2 times 1, negative 1. The dot product says 5. And if you take 4, 1 times 1, negative 1, the dot product is going to say negative 4 minus 1, which is negative 5. 5 and negative 5, if you factor out the 5, you're going to get 1 and negative 1. This, of course, is 5 times that vector x right here, where this was a times x. So the first column of P is an eigenvector, and same thing right here. If we take the second column 1, negative 2, let's say that's the vector y this time. If we take a times y, well, going through the multiplication there, 7, 2 times 1, negative 2, you get 7 minus 4, which is a 3. And then the second row times the column, you're going to get negative 4 minus 2, which is a negative 6. And so factoring out that 6, second out the 3, excuse me, you're left with 3 times 1 and negative 2. And that's, of course, 3 times y. So we can see that the two columns of P are eigenvectors for this matrix A. And in fact, 5 and 3, that looks familiar. If you look at the diagonal matrix D, was it not 5, 0, 0, 3? 5 and 3 are the diagonal entries of this diagonal matrix D. And remember, if you have a triangular matrix for which diagonal matrices are triangular, diagonal matrices are those which are upper and lower triangular matrices. The diagonal entries of a triangular matrix, or in this case a diagonal matrix, these are the eigenvalues of the matrix D. And when matrices are similar, they have the same eigenvalues. We had talked about that before as well. They have the same eigenvalues. And therefore, if A is similar to a diagonal matrix, it'll have the same eigenvalues as that diagonal matrix, and those eigenvalues will be just the diagonal entries of the matrix. So I want to kind of summarize these principles we talked about in this specific example here. This works in greater generality. If we have a matrix A, which is n by n, that matrix A will be diagonalizable if and only if A has n linearly independent eigenvectors. That set of n linear independent eigenvectors is called an eigenbasis for the vector space. All right? And so it'll be diagonalizable if and only if you have enough independent eigenvectors. Okay? And so if you have an eigenbasis, then you can construct your diagonalization in the following way. D will consist of the diagonal matrix whose diagonal entries are the eigenvalues of A. So you just put the diagonal entries, you just put the diagonal entries of D to be the eigenvalues. And then the matrix P will be the matrix whose first column is x1, whose second column is x2, whose third column is x3, up to this nth column, xn here. And we have the property that ax1 is equal to lambda x1. So x1 is an eigenvector where lambda 1 is its eigenvalue. And ax2 is an eigenvector of A whose eigenvalue is lambda 2. And you can proceed in this pattern getting axn lambda xn. So you can construct this matrix P using your eigenbasis. That's what this is right here. You have your eigenbasis. That forms the columns of P. You have your eigenvalues down the diagonal. You have to go in the same order. The eigenvalues and the eigenvectors have to correspond to each other. And if you have this eigenbasis, you can construct this non-singular matrix P, and that's how we can form this diagonalization. All right. Some things I want to mention here to make some connections to things we've talked about in the past. If you have an eigenbasis B for the matrix A, and if E is just your standard basis for Fn, so this will consist of like E1, E2, up to En, that basis right there, then this matrix P is just none other than the change of basis where you switch from the eigenbasis to the standard basis. And hence its inverse matrix will be the change of basis matrix from the standard basis to the eigenbasis. Make a connection there. And also another sort of nice result here is that if a matrix has n distinct eigenvalues, then it's always diagonalizable. And that's because we saw earlier that for distinct eigenvalues, the eigenvectors will automatically be linearly independent. So if you have n distinct eigenvalues, you'll have these one-dimensional eigenspaces, which are all pairwise independent from each other. And so you always get an eigenbasis using that. The only time that you're not diagonalizable is if you do not have enough eigenvectors, and that would only happen if you have repeated eigenvalues. Now, that's not to say that if your eigenvalues repeated, that you can't have an eigenbasis. You certainly can. We'll actually see that in the next example coming up. But you might not have enough eigenvectors if there are repeated eigenvalues. Basically, the issue here is you're going to be diagonalizable if and only if your geometric multiplicity, which is the dimension of your eigenspace, is equal to the algebraic multiplicity. And the algebraic multiplicity, this is the amount of times a eigenvalue shows up in the characteristic polynomial, and we want this to happen for each eigenvalue. That's exactly the conditions that will guarantee we have an eigenbasis, and hence we're diagonalizable. All right, so then the last part of 6.3, which we'll watch in just a moment, we'll actually see an example of how you can diagonalize a matrix. It's kind of an extensive problem, so we're going to do it all at once. See you then. Maybe go to the bathroom beforehand. It takes a little bit to do.